Okay, we will go deeper into chemistry today. We will actually write some equations that are directly pertinent to chemistry. But the general mathematical topic that we introduce today is hugely important. It is differential equation. And it's important because most of the current models of reality that we have, quantum mechanics, hydrodynamics, quantum field theory, and so on, are formulated not in terms of algebraic equations, but in terms of differential equations. So what we will hear today is actually the foundation of modern understanding of how the universe works. But at the level of the chemists, you will see it almost immediately in anything that you do when you start laboratory practicals, for example. If you have some vessel or reactor, let's call it A, then some chemicals will be arriving into that reactor at some rate K1, and then as things happen inside it, a certain amount will be wasted, KW1, and a certain amount will be transferred over into the second reactor, B, and then some of it will go out, and some of it will get wasted again, so K waste 2. And you can see that such a schematic pertains not to the concentration itself, but actually to the rate of change. That is, we are adding the chemical A at a certain rate. It is being moved at a certain rate. The more there is, the more will be moved per unit time. It is wasted at a certain rate because it's a fraction, or it is wasted in kilograms per second. In all cases, we are not actually looking at the quantity A of t directly. We are looking at the quantity A prime. At what rate it is introduced, at what rate it is wasted, at what rate it disappears. And so it stands to reason that the equations describing something like this are going to involve the function itself and its derivatives. And what is unknown here is, in fact, A of t, whereas that is usually known. So how do we reconstruct the function when we know its derivatives and relations between its derivatives? This is the subject known as differential equations. Now, interestingly, the best way to introduce it is not, in fact, chemistry. The best way to do it comes from population biology, which is very, very closely related, as you will see. So let us consider a fairly basic biological system on which some grass is going to grow. So grass, it's growing there, and sun is shining down upon it at a constant rate. So let us ask ourselves, what is going to be the rate of that growth? D quantity of grass by dt. Well, clearly the solar radiation is arriving at a constant rate, right? It's a fraction of a kilowatt that's shining down, and so the photosynthesis can only proceed at a constant rate. And so the rate of grass growing, as agriculturists would know, is a fixed number of kilograms per day, or per year, or per whatever unit time. So dg by dt will be increased by a certain constant, k grass growth. The grass grows at a constant rate. But then, of course, what will happen is individual plants will be reaching the end of their lives, and they will be dying off. And eventually, the more grass there is on the lawn, the more will be dying per unit time. And so the rate of grass departure, so K grass death, is actually proportional to the quantity there is. So we have to G into here, and a minus sign because the rate is negative. The grass is actually dying out. What will, of course, also happen is the grass has a predator. On the same lawn, there will be rabbits who will be eating that grass. Okay. Munching it up. And the amount that's being eaten per unit time, so let's say that the rate grass being eaten, will be proportional to the number of rabbits there is, but will also be proportional to the quantity of grass. So if there's more of grass around, they'll be feasting on it more, or at least so goes the approximation. It is an approximation. So insofar as d grass by dt goes, this is a negative contribution because it reduces the total rate that is arriving. So k grass being eaten will be then followed by the quantity there is and by the local concentration of rabbits. So the more grass there is and the more rabbits there are, the more is destroyed, hence the minus, per unit time. Okay, but of course that's not the only process that happens in the system. What about d rabbits by dt? Well, if 2 rabbits meet and there's a sufficient quantity of food available, so rabbit number 1, rabbit number 2, and there's enough food that is being present, the predictable thing happens, right? And more rabbits are produced. So what we have there is a certain rate, k rabbit burst, which will be proportional to the number of rabbits there is, also proportional to the quantity of food available. So with a plus k rabbit burst, the more rabbits there currently are, and the more food there is available, the greater that rate is going to be. What will also, of course, happen at the same time is that these rabbits will be shuffling their mortal coils off and become X rabbits at a certain rate, and so there will be k rabbit death. And the more rabbits there are, the more will be dying per unit time, and so we have minus k rabbit death times the quantity of rabbits, in the same way as we had the term for the grass. The more there is, the more dies per unit time. But then, of course, there will be further parameters in the system, and this rabbit has got some small probability of ending up as a dinner of a fox. A fox. And that will be consuming the poor, unfortunate rabbit. So k rabbits being eaten. And that's a negative factor in the rate of rabbit proliferation. So minus k rabbits being eaten. Clearly, the more foxes there are, the more rabbits will get eaten, and the more rabbits there are, the more likely they are to meet a fox. And so this will be the concentration of the rabbits times the local concentration of the foxes. And the final thing we need to do is defoxify. And foxes do not have natural predators in Britain, right? Not now that we're not hunting them anymore. And so they will be dying just a natural death, but what will of course happen is that they will be proliferating. Okay, so we put the second fox around here. These two meet, watch some Netflix together, and if there's sufficient food available, in terms of some unfortunate rabbits being around, right, so the predictable thing again happens, and we've got more foxes. So, dfox by dt is plus k fox first, quantity proportional to the quantity of foxes available, proportional to the quantity of the rabbits available, and they will be dying at some rate. K minus k deaths times the number of foxes. Now, as you can see, the picture is not terribly bright for the rabbits. They've got a choice of death or being eaten, so they might be, protesting and passing legislation. But they'll get eaten anyway, right? In any competition between biology and ideology, the winner is predictable. And since, well, we are coming up to an election, right? The rabbits in this picture will probably vote for Jeremy Corbyn, and the foxes will probably vote for Boris Johnson, and this is the decision that all of you will have to make. Which side of the food chain you are planning to end up on. But this is a system of differential equations, and the topic of today's lecture is learning how to solve these things. You can see how easily we could transpose this onto chemicals. Right? Chemical one arrives at a steady rate, and it can produce something else, polymerize, for example. It can be lost irreversibly because of the wastage, or it can just transmute into something else, in which case something else happens. So the numbers of rabbits and foxes in here could easily be interpreted instead as concentrations of rabbits and foxes, at which point we're dealing with chemistry. Okay, so let me give you a few examples of less complicated differential equations than the one we've got here. You have a machine-generated solution. It's called Lotka-Volterra predator-prey dynamics. It's really complicated. But let's focus on something simple. So item number one, simple. Let's take a look at the radioactive decay. We have a slab of plutonium on the table or something like that. And so D, concentration by dt, well, the more plutonium there is, the more is destroyed per unit time at some rate. Minus K times C. Where C is the concentration or quantity of plutonium. And perhaps C is not a good letter in here, we just call it A, because we will be using C to denote various constants. So the first derivative of A must be proportional to A itself. Do we know any function that when we differentiate it returns itself? Exponential, right? It's actually easy to show that that is some arbitrary constant e minus kt. If I take this function and I differentiate it, a prime of t, that will be c k e minus kt with a minus sign in front. And that is actually the same as A of t, except for the minus k. So you see, this function satisfies this equation. And so this is called a differential equation. And that is called a solution to a differential equation. It's the unknown function which occurs within it. This is a conceptually different thing to what you have seen previously. Previously, your unknowns have been numbers. You had things like x plus y equals 3 and x minus y equals 2, and then you will have to find the numbers. Here, the unknown is a function, and so we will find it considerably harder, of course, to determine what those functions are. Notice also that there is this arbitrary constant in here. This is always the case in all differential equations, partly because constants vanish on differentiation, and so there's certain liberty in here. But also, and this is also important because, of course, we've only got pretty much one serious equation of motion that here on Earth, at the energies that we typically encounter, describes what we do, Dirac-Schrödinger's equation. And it is essential that to that equation there be a multitude of solutions, not just one solution. Because I'm a solution to that equation and you are solutions to that equation, but with different settings, initial conditions, and so on. And so these coefficients, in fact, provide the essential liberty to enable all the varieties that we see in the physical reality around us. So they are very important, these constants, and we will also learn how to get them. So this because it only involves one derivative, is called an ordinary differential equation. I gave you partial derivatives for a good reason in the previous lecture, because there are also partial differential equations. Let me give you an example of that. The equations that will be haunting your dreams for years and years after you start learning serious quantum chemistry is the Schrödinger equation. Psi by dt, note partial derivative with respect to time, minus h bar squared over 2m d2 psi by dx squared, where psi is a function of coordinate and time. This is a one-dimensional Schrödinger equation for a free particle of mass m. As you can imagine, it would be considerably harder to find out what this psi actually is, because its first derivative with respect to time must be proportional with some strange proportionality constants, this is Planck's constant, to the second derivative with respect to space. And it's not obvious by just looking at it what that solution is going to be. But let me show you a sort of more prosaic example, the equation that describes strings of musical instruments. So d2f by d in this case t squared is minus omega squared f of t. That's an equation that is satisfied by quite a few oscillatory processes. We can posit, for example, that f of t would be what I choose here, sine omega t. That the string of the instrument is sinusoidally modulated after somebody's plucked it. And indeed, if we take a second derivative of sine, so f prime of t will be omega cosine omega t, then f double prime of t will be minus omega squared sine omega t, at which point we have the original function but with minus omega squared in front, and that satisfies. So that is in fact a solution to this equation. So that's the setting. These are a couple of examples of equations and solutions. We also note here that we have these indeterminate constants, and the way we find them out is by using extra information that is always available in physical settings. So that information is called initial and boundary solutions. So topic number 2, initial. Consider our plutonium example there. So we solved this equation somehow. I'll teach you exactly how to do it, but we've got the solution. A of t equals some constant e minus t. And that's our plutonium. However, what we also know is how much we had at time 0. So our quantity at time 0, to 0 in here, was some fixed quantity, a kilogram, a ton, whatever it is. But we knew how much we originally had. We can use that information to determine this constant, because a of 0, if you put time to 0 in here, the exponential disappears, a of 0 is actually c. If you compare that with that, you discover that the constant is actually enough, which gives you the law for radioactive decay, which you have all seen at school. K of t is the original quantity, E minus kT, where K is the rate of decay for the radioactive substance. So we have quantity A0, somebody else could have had a different quantity. Right? This is why differential equation has these indeterminate constants, because everybody's constant will be different. Ours is A naught, whatever quantity we had, and so our solution to this equation is this one. So the solution that contains these unknown constants is called the general solution, because it describes every possible case. And every possible realization of the process that the equation describes. That is general solution. That is the specific solution that is pertinent to our case, without specific initial condition. And so that is called particular solution. Initial condition is not the only type of information you can have. You might not know how much you originally had, but you might know how much you had at a certain time. In which case you just put the time in there, this quantity in here, and that still allows you to extract C. Or in the case of a string of a musical instrument, we can say that the string has been clumped at the beginning and the end, as it happens in most musical instruments. It cannot actually move from those ends, in which case the coordinate of that string has to be 0, the y coordinate, at those points. Things like that are called boundary conditions. For example, if we have A at some time, I don't know, T3 or whatever. So if any information is provided about what that solution had been, usually this is experimental measurements. So spectrophotometer measures the concentration at certain specific times, and then you would like to constrain the solution to differential equations. These will be the boundary conditions of what you have. Okay, but enough introductions. Let us just go into the recipe of how one goes and solves a differential equation. I have an actual line-by-line example in the case. So that's item 3, solving ordinary differential equations. Solving the partial ones, like Schrödinger's, is the second semester. It's Chem 2024, where I spent, I think, 3 lectures solving hydrogen atom and getting all the orbitals and so on in the mathematical form. That's a really long story. Okay, so the first thing you need to do, if you have an equation, so A is bring the equation into form f of x dx equals g of x d of y dy. That is, you need to collect all variables of one type, coordinate, time, whatever it is, on one side of the equation with a differential, and all the variables of the other kind on the other side. So to give you an example, if we have dA by dt minus ka, well, I told you already that because these are actually differentials, you can treat this as a fraction. So we multiply this by dt, and we divide this by a. The result will be dA over a equals minus a dt. This satisfies our requirements because the variable a has all been collected on the left-hand side, and the variable t all ended up on the right-hand side. So this is called variable separation. Not all differential equations are separable. Considerable effort may be required, but the simple ones are separable, the ones that you will be dealing with in your chemical context. As for the more complicated ones, books this thick have been written about differential equations, and so necessarily, because it takes a little time in this course, we only deal with the simplest cases. Okay, so bring that into that form. The second item is integrate both sides. We will go through the process of integration in great detail a few lectures from now, but for now I'm just relying on your school memories of what it is. To integrate is just the reverse of the differentiation. So we do the following: integral x dx equals integral g of y dy. And if you know these functions, you would be able to integrate them. In that particular case, integral dA over a is minus integral k dt. Well, you remember the derivative of the log was 1 over, and so the integral of 1 over is the log. So what we have here is log a plus a constant, one of them. And then on this side, the derivative of kt was k, and so the integral of k is kt, but don't forget the constant, minus kt plus a different constant. Okay, so what we will do is we will move that over there. So log a is minus kt plus c2 minus c1. Well, actually, the sum of a difference of two constants is just another constant. So that we will call c. Right? Then what we can do here is we can, well, try and solve this for a. That's exponential. Exponential of the log will be just a, and a function of time will be e to the minus kt plus a constant. Some further cosmetic simplifications are possible here. Exponential of a sum is a product of two exponentials. A of t is e to the c times e to the minus kt. And the exponential of a constant is just another constant, right? So we can just ignore the presence of the exponential. So we will call that either d. D is e to the c. D e minus kt. And that's our general solution that you have already seen for the radioactive decay. And then the third step is to find out what this constant is. And so that's item C. Using initial or boundary conditions, find all constants. If the equation involves only first derivatives, there will be only one constant there. Again, in the second semester, we will move to situations where there are multiple constants and multiple derivatives with respect to multiple variables. But those are real hard, those cases. I think, again, it takes me an entire lecture to solve the differential equation, even in the most basic possible case. Okay, so you find the constants, and that means that you have the complete solution that is actually specific to your initial boundary conditions. And the last extremely important step that people skip, but it's not a good idea. Check the solution by back substitution. Simply speaking, just put your result into the original equation and make sure that this function, when you differentiate it, satisfies this equation. Simply do is then say, okay, let's say we've got this to a0, so that's our particular solution. And let us now check. So on the left-hand side, I will differentiate it. So it will be minus k a0 e minus kt. And on the right-hand side, I would simply substitute minus k and then that a0 e minus kt. Indeed, the left-hand side is equal to the right-hand side, and so we are convinced that this is indeed a solution. This is very important because this process is quite protracted. It will take you some time to achieve the level of reliability in your mathematical transformations when you're not dropping minuses or constant factors and so on. And that's the way of catching an error. If that doesn't check out, that's a signal, okay, recheck your arithmetic. In some cases, that's also the way to solve, because on quite a few occasions, people simply guessed the solution to the differential equation that I gave them, said, okay, I think that's the solution, plug it back, demonstrate that that's a solution, that's a valid way of solving it, like full marks for that. Quite a few physical problems, including really serious ones like Schrodinger's equation, the solutions have been guessed. and then publish. Valid way of checking. Okay, so this is our recipe, and let us now solve a nice proper differential equation. Again, the flow chart to work. So we have an equation that is dy by dx is x plus 10 sine x, where we know that y of 0 was equal to 0. So some kind of oscillatory process for which the instrument has returned us the stiffness of the slope. So some instruments are only sensitive to the slope rather than the altitude of the ground, for example. And so we dragged that instrument across some spatial profile, and it returned us a certain function which returns us the slope of the ground. And then also we came around with a ruler and measured the function at the location to 0, and we discovered that it's actually at 0 altitude. So what is the profile of the actual ground? We start here. We need, by any transformation, pair or foul, to bring it into the form. Like one variable is on one side and the other is on the other. In this case, quite simple. We can just multiply both sides by dx. But actually finding out what these transformations are is a creative art. There's no fixed recipe. This is where mathematics becomes interesting. And you will see examples where it takes considerable effort and ingenuity to actually separate variables. But in our case, it's simple. dy is x plus 10 sine x dx. And it does bring it into this form here, where g is 1 and f of x is the same in brackets. Okay, so item B, we now need to integrate both sides. Integral dy is integral x plus 10 sine x dx. You've done integration at school. You will do plenty more integration, take my word for it, in this module. But that is just y plus a constant. First one is integral of x is x squared over 2. Integral of a sine is minus cosine, minus 10 cosine x, plus another constant. As I've already mentioned, sum difference of two constants is just a single constant, and so our y of x here is x squared over 2 minus 10 cosine x plus some constant. And that is the general solution to our equation. General because it accommodates a multitude of initial conditions because of that constant. And now we plug in the initial condition. We know that our y at 0 has been 0. Y of 0, here's the thing. X squared over 2x0 is 0. Cosine x is 1, and so that's minus 10, plus a constant. So this is the value of this for x equals 0, and it has to be 0, as per the information we were given, 0, from which it follows that c is equal to 10. And so our final thing is to write that particular solution that is specific to our case. Y of x is x squared over 2 minus 10 cosine x plus 10. The final thing that we need to do is to actually check. So we put it back into there. So dy by dx from our solution there is x minus plus 10 sine x. And the constant differentiates to 0, and x plus 10 sine x is actually exactly what we had on the right-hand side of there. So this is indeed the correct solution. So what I did was to take the equation, to separate the variables as prescribed, to integrate both sides, to arrive at an algebraic equation now for our unknown function with some unknown coefficient. Then, from my knowledge of the initial condition, I know that that solution at x equals 0 must be 0. So I put x to 0 and I equate the result to 0. That gives me the value of the constant. Constant goes in. That is the particular solution that is specific to our initial condition there. That's the profile of the ground that you have based on that information, that equation, and so on. I think I have another example. Yeah. Let's just make some space on this board. Let's leave our recipe there. So this is now going to be an example where the separation of variables is not instantaneous, where some mathematical transformations must be applied in order to make it possible. So we are told that dy by dx is the following fraction. It is x plus y over x. It's not obvious here, but at least from the immediate appearance of it, but no amount of fiddling with this equation is going to separate the variables. You will always find that x and y are inextricably entangled here, and it wouldn't be possible to actually split the two no matter how hard you try. Thankfully, the problem tells us that we must use the substitution u equals y over x, or equivalently y equals ux, to introduce a new variable, and that will split the equation up. Well, what do we need to do? We need to first replace all variables, and it's easy enough to replace y with ux here. But what is also necessary is to replace the differential. And this is why I taught you the differentials in the previous lecture, because they occur in these equations. Okay, so our objective, as per the problem text, is to replace all instances of y with ux. So y itself is straightforward, but dy, well, you actually know what to do with it, right? It's u dx plus x du, the product rule. And we've practiced that in the workshop. Okay, dy goes on top. U dx plus x du over dx equals x plus ux over x. And let us see what is going to happen once we simplify this. Dx over dx is just u plus x du by dx. So we have a derivative of u with respect to x. And on the right hand side we have 1 plus u. So far so good. Well, u actually cancels on either side. So we have x du by dx equals 1. But that is actually separable. If we multiply both sides by dx and divide them by x, what we will get is du equals dx over x. And that's nice, because all the u's are on one side and all the x's are on the other. Let me see if I got everything right in my handout. Yeah, I did. So this accomplishes step 1 in this procedure. The original equation could not be brought into this form. We will struggle with it in the workshop. And we were suggested a transformation, in this case a differential transformation, hence my introduction of differentials to you in the previous lecture, that actually does it. Okay, so what we now need to do is solve this with respect to u and then reverse that transformation. So, integral du integral x dx. This is just u plus a constant. This is log x plus a constant, constant 1, constant 2. And so the general solution for this is that u equals log x. But remember that u itself was y over x, and therefore what we now need to do is to reverse that substitution. So y over x is log x plus a constant. And therefore y is x log x plus cx. And you see constant here is actually not a free constant, it comes multiplied by the variable. And this is our general solution. We are told to not compute the particular solution. The problem doesn't particularly care about it, so we just keep it general. But the last item still stands. We must substitute this back and check. So dy by dx will be equal to, well, we have the product rule, so we will have log x plus x over x plus c. So we have substituted that back into there. And, well, it simplifies. So it's log x plus 1 plus the constant. And then what we would need to do is put this derivative over here and put our solution over there and check whether that's actually true. Now I'm running out of time and I've got one more thing to tell you, so I'll just leave it to you as homework to put this on the left hand side, to put y on the right hand side, to do the mathematical transformations and to demonstrate that that is in fact correct. Okay, so one last type of solutions to differential equations that you will see a lot in chemical kinetics are something called steady-state solutions. Those are solutions that pertain to situations when chemical equilibrium is assumed to have been achieved. So you put some chemicals into a flask, you leave it for an infinite period of time, you come back after that infinite amount of time has passed, and you check the flask. And you will have your systems of equations described by differential equations. Well, let's just write something fairly basic. So you will have A going forward into B and going backward into A. So that's K plus and that's K minus. And it stands to reason that dA by dt, the more A there is, the more will be consumed per unit time. So minus K plus A. But the more B there is, the more will be returned into A per unit time. So plus K backwards B. And then dB by dt is the more B there is, the more will be consumed into A per unit time. So minus K backwards B. But the more A there is, the more will be forwarded to B per unit time. So plus K forward. And this, despite its relatively compact notation, is a horrendous system of differential equations, right? We've learned to solve single ones in here. That's a system that's real hard. However, after an infinite time has passed, there was a song by Rexette, before you were even born, called Never Is a Long Time, and it is in this case. What happens is the concentrations stabilize. They stop changing. As soon as concentrations stop changing, these derivatives go to zero, right? So at the steady state, or more precisely at equilibrium here, we actually have a system of algebraic equations. So 0 equals minus A plus A equilibrium minus A plus A minus B equilibrium. And so 0 is minus K minus B equilibrium plus K plus A equilibrium. But this is wonderfully nice because we can actually now solve for them. Both equations turn out to be saying the same thing. They're just one multiplied by minus 1 relative to the other. But if we take, say, this over to the left-hand side, we get K minus B equilibrium equals K plus A equilibrium, and we can then figure out that B equilibrium over A equilibrium is actually K plus over K minus, and you have seen this equation already when we took infinite time limit in the lectures that I introduced to the limits here. So these equilibrium solutions, or steady-state solutions, because they involve algebraic rather than differential equations, tend to be considerably simpler. And those of you who have gone enough in chemical thermodynamics by now will actually remember that that's the definition of the equilibrium constant. The forward rate divided by the backward rate. So that's the connection to chemical kinetics of everything that I have told you. Okay, a summary of the lecture is when we build chemical models, we literally build them in exactly the same way as I built the population dynamics model for you. You just write that down and philosophize until you have the right equations. As soon as you have the right equations, well, all hell breaks loose, to be honest, but in simple cases, you can solve simple ordinary differential equations with this procedure. Right? Follow the flow chart, and every step is understandable, one foot in front of the other, and you will get to the solution. Do not forget to double check your solution. So I gave you a few examples, and the principal application of all of that, the chemists may already have got to that. If they haven't, they will, like literally next week. They will introduce chemical kinetics, and then you will be solving these equations till